Hello, Singapore. It's great to be back once again. So my talk is called Making It Rain, Advanced Special Effects with SwiftUI. Now, this is a particle. It is a small white blob, and it looks pretty boring. I know it does. And if you zoom up really big, it's still really boring, okay? There's nothing special about it, just a simple blob picture. But if you make many of these things and make them move, you can get lovely effects like snow falling down. Or if you overlay them and color them, you can make fire burning. Or make them scale up and fade out. You can create fireflies. Or change the blob for stars and add some color, you get magic. They're very flexible things. And in fact, they're most famously used by Apple in the weather app to make rain and snow effects. So when you're out in Singapore getting soaked in a famous rainstorm here, at least you admire Apple's commitment to detail. Now, if you're an iOS Conf SG regular, you might know a talk I gave 2 years ago. Just plain old special effects with SwiftUI, not advanced, just plain old special effects. And this was building a very, very small particle system with SwiftUI, using things like core motion to do tilt detection, even AirPods. It was great fun. But then last year, at WWDC23, Apple announced they're bringing a particle system to RealityKit. The ability to make amazing, beautiful particles in 3D. But only for Vision Pro. And so you want to make great 3D games that run on Vision Pro, you're in a great place. You're set. But if you want to target iOS or use regular SwiftUI, you're basically out of luck. So I thought, is it possible to take everything from my earlier particles work, add in some great things from RealityKit's particle work, then make it work on all Apple's platforms with SwiftUI in one 30-minute talk? Should we find out? As you break this task down nice and small, you get these 10 core things to work on. I'm going to walk through these things step by step, one at a time, starting with drawing. And this first one takes the most work, so I'll break this down to 4 smaller steps. Step 1, we're going to decide what's stored inside a single flake of snow. What does one particle need to have? And we'll start simple. We'll say there's a structural particle, and it has a position. Now this thing, SIMD2, comes from Apple's SIMD framework. It's, of course, short for single instruction, multiple data. Lets us do mathematics much more effectively. And this position will be stored in a range of 0 to 1, where 0 is the top or left edge, and 1 is the bottom or trailing edge. Step 2, what should be stored inside a single particle system? Well, we know a system is a collection of particles. So we'll say, well, let's give it an array of particles. And also, it'll have its own position. Again, a SIMD2 with a default value of 0.5, 0.5. So it's centered in the screen. And again, we're going to add more to this later on, but it's enough for now. What? So, if you've met me already in this talk, you'll know my daughter's accompanying me to Singapore. She's worked very hard on me with this talk, and she's now pointing out things I forgot to say in the talk. Thank you, Sophie. She's asking, why is it a class? The other one was a struct. Okay, so the particles are structs because we'll be making them, throwing them away regularly as we're making new particles. The class will make once and share the entire time, okay? Yeah. She's only 13, give her a, she's trying her best. So, inside this class, we're going to add some code. Again, a little bit for now. We're going to say inside here is a create particle method to make one particle. This will make a new particle at our current position and add it to the array. Real simple. And we'll also add an update method here. Again, it'll just call create particle. So whenever we update the whole system, just make a new particle. Nothing fancy. Step 3, now we have that, we'll make a simple view to render our particles. This will isolate all our drawing functionality in one place and make it easy to place particles in our apps. So make a particle view. You can see it's got some state to store our particle system, but it's not making it there because it'll be passed in externally in an initializer. Let's stash it away. Here's the system we want to draw. Fog, smoke, whatever it is. Put it away. And then inside there will be a draw method to draw our particles. And you can see it says, what should I draw? Well, it's this particle system here. Then where should I draw it? Into this SwiftUI graphics context from a canvas. And also a size. Now, the size matters. Remember, we're storing our positions in a range of 0 to 1, not absolute screen coordinates, just left edge, right edge, top and bottom edge. And we're going to multiply that by our size to get a correct particle location in screen coordinates. Inside there, we can loop over all our particles, one at a time, get the correct x and y coordinates, again, multiplying by size, and then simply draw that to the screen at the location. And once we have that, it means our particles are on the screen correctly, and everyone's happy. What now?
What is the dot circle?
Oh, that's fine, all right. In Xcode 15, folks, haven't seen already, when you added images before, you have to use strings everywhere. Image, quote, circle, quote. In 15 onwards, it makes these nice constants for you. I can just do image.circle from the asset catalog. It compiles it for you. It's very nice. Entertaining as it is being interrupted all the time, do you want just, like, if you can do a better job, you want to do it? Come on then. So, you can, this is the clicker. Here's your microphone. I shall be just here if you need me.
Okay.
Best of luck.
And finally, we need to fill in the body property for our animation view. This is a timeline view set to an animation schedule, which means it redraws at least 60 times a second. And inside there is a canvas view, so we can do all our custom drawing. This gives us a context we're drawing into, plus the canvas size. Inside the canvas, we first tell our system to update itself. Right now, this just creates a new particle. And now, we can call the draw method we wrote a few minutes ago, passing in the particle system, drawing context and canvas size. That's all the hard work done. So now all that remains is to update the main view for our app, so that it creates a particle system and passes into our particle view. So, in the content view, we'll make a create system method that creates a simple particle system. We'll add more to this later. Then, in the view's body property, we'll pass our particle system into a particle view, and we're done. And that's our first step done. It was quite a lot of work, but it really gave us some great foundations to build on. Of course, you're probably curious, after all that work, how does it actually look? Do we have snow falling beautifully in the sky? Can you make fire? Well, no. Instead, we have this. This is actually a video, by the way. It's just really dull because nothing is happening. At this point, you might have some regrets about coming to this talk, but stick with me. Let's tackle the next feature, making the particles move. This means adding a new property to our particles to store its x and y speed. Then, in the create particle method, we pick a random direction from 0 to 360 degrees, which in radians is 0 to 2 pi. We can then use sine and cosine to convert that angle into a movement amount and pass that data into the initializer for our particles. So now each particle knows how fast it should move. Now for the important part, actually applying that movement. This is our current update method, and all it does is create new particles. We need to change it so that it moves all the existing particles too. So, we're going to call compact map on all our particles. This allows us to take the current particles, transform them somehow, and return a new array of modified particles. First, we take a copy of the current particle. Then you modify its position based on its speed. This is an example of why SIMD is so important. It adds the x speed, the x position, and the y speed, the y position, all in one operation. Then we send back the modified particle. And that is moving done. Of course, you're probably suspicious at this point, and you should be, because here's how our code looks now. The screen is completely blank. Yes, this is another video. It is just completely blank all the time. Now, our original circle might have been boring, but this is somehow even worse. If If you remember back to high school mathematics, the sine and cosine functions always generates values in the range of -1 through to 1. We're using those two with our launch angle to calculate the x and y speed for our particle, which means the x and y speed will be in the range of -1 through to 1. And every time our particle system method update is called, which is at least 60 times a second thanks to our timeline view, we add that x and y speed to the particle's x and y position. Now, remember that our screen positions are measured in the range of 0 to 1, where 0 is the top or left edge, and 1 is the bottom or right edge. So, we're creating particles in the center, which is x 0.5, y 0.5. We're then adding some value between -1 and 1 to both the x and y position of the particle, causing it to fly off the screen, but it's even worse than that. Because the screen redraws 60 or 120 times a second depending on your device, the movement gets applied 60 times a second too. This means each particle flies off the screen in the very first call to update and continues to fly further and further off the screen. We can solve this using a technique called frame-independent movement, which means we move our particles by different amounts depending on how much time has elapsed since we last moved them. As an example, let's say we want to move 20 points right. 1 second has elapsed since the last update, 1 times 20 is 20, so we move 20 points right. This works for all speeds, so if a quarter of a second has elapsed, it would take 4 updates to get to the destination, like so. This means our particles automatically move faster when updates come less often, and move slower when updates come more often. Overall, this means it'll move at a fixed speed no matter how often update is called. This starts by adding a new property to our particle system to track the last time update was called. Then, in our update method, we can convert the current date to the number of seconds have elapsed. If we subtract the last update from the current time, it tells us how much time has elapsed since the last call. This is our time delta, our difference that we need to use for all adjustments, so we make sure they happen at a fixed speed. And then we can stash the current time in our last update property, so we use the next time update is called. Finally, we multiply that into our x and y adjustment, so x and y speeds stay fixed, but the actual amount of movement applied depends on how much time has elapsed since the last update was called. And here's the result. We have actual particles flying around the screen. I know, it's not very exciting, but we're getting there. Our next target is varying. What if our particles could be made at different sizes, move at varying speeds, and live for varying lengths of time? These changes should make our particles look a lot more natural. This means adding a bunch of new properties to our particle system, starting with how long particles should live for, measured in seconds. Then, how fast particles should move, and how big particles should be, where 1 is 100% the size of the image. This will store how much to vary lifespan by, measured in seconds, and applied as a range around the base lifespan value. Then, we have the same thing for speed. Again, this variation is applied above and below, and size variation too. We're also going to add a third size property to control how size varies over time. This allows us to make the particles get bigger or smaller as they age. We need to add 4 matching properties to our particles, starting with the time this particle was created. Then, how long this particle should survive for, and how big the particle should be when it's created. And also how big the particle is right now. This can be set to 0 here, because it'll be calculated every time update is called. To make our code easier, we're going to add a small extension to double. It's called spread, and it generates a random value from our variation. Again, half the variation is applied above the basic value, and half is applied below. And now, we need to adjust the create particle to take these properties into account. So, the speed for this particle is some base speed plus some amount of speed variation. Then something similar for our lifespan, and for the size. Inside the create particle method, we can apply the new speed immediately. Then we can send the other values into the particle's initializer. Inside the update method, we need to change the way we're updating each particle. This is our current code. We need to put some new code here to calculate each particle's current size over time. This means we first need to see how old the particle is, which means subtracting its birth time from the current time. We can then see how far the particle is through its life by dividing its age by its lifespan, giving us a value from 0, just born, to 1, dead. We can calculate the particle's end size by multiplying its start size by size at death. And now, the gap between the target size and start size is how much it needs to grow or shrink over time. Finally, we can calculate the particle's current size as being sum size between its position and its start size, target size. But what happens when it's dead? Well, if the particle's age is greater than its lifespan, we want to remove it from the list of active particles. In our case, that means sending back nil rather than copy. This is why we used compact map earlier, so we could remove dead particles. When it comes to drawing our particles, it's important that we move the correct location before scaling, otherwise it'll make the movement bigger or smaller too. So we can't just use this. In its place, we're going to take a copy of the graphics context and move it to the correct location. We don't want to change the location of all feature drawing, just this one particle. We can then scale it down to the correct size, so we move, then we scale. And finally, we can draw the particle. Now that we're already in the correct location, we can use 0 for the draw position. And that completes all our code changes, so we can now use this in our particle system. If you remember, this is the create system method we put into content view. We can now add values into there to customize the particle system using our new properties like this. This means our particles will have a speed between 0 and 0.4 and a size between 0 and 1. This means the particles scale down to 0 as they age. And here's how it looks. Particles are all different sizes and speeds. And that's varying done. Now, be honest. At this point, I know what you're thinking. This is a lot of work, and this is the worst talk ever. But sadly, they locked the doors, so you're kind of stuck now. So, let's go on to our next topic, falling. How can we apply gravity to our particles? First, we're going to add a new property to our particle system to store acceleration. This is the SIMD2 with x and y values of 0. There is no acceleration by default. This is how our update method updates the x and y position for each particle. We need to account for acceleration here too. We're going to adjust the particle speed based on the acceleration, so the speed changes with every update. Remember, we need to multiply by our time delta to get frame-independent speed. And now, when we create our particle system, we set acceleration of x0, y2, and all Apple SIMD types can be created using arrays like this. And here's how our code looks. It took just one new property and 2 extra lines of code in our update method, and it looks great. So that's falling done. Next is a really interesting one, tagging. We're always using the same image right now, but wouldn't it be nice to make that more customizable? Here's our current drawing code. It always draws the circle image. And here's a canvas we're currently using inside Particle View. Well, SwiftUI's canvas can accept a list of symbols to draw. These symbols can be any SwiftUI view. So, we can place our circle image into there, but there's one catch. We need to give it a unique tag so we can refer to it in the code. But just adding a name like view is fine for now. But then what should go here? Well, first, we can find the correct image to load by looking up its tag in the context, like this. And now we can draw that instead of the image we used previously. Here's the result. It's literally identical. So why bother doing all this extra work? Well, it's identical because we're sending the same image into the canvas to be drawn. But we don't need to anymore. We can send any SwiftUI view in. So, we could switch the image out for an emoji with a custom font size, and now we have unicorns everywhere. So that's tagging done. Or is it? Yes. We're still able to pass a custom view into our particle system, but that's still being decided inside Particle View. Right now, we just create a simple particle view, and inside there is code to decide which symbols to use. A better idea is to send the views to render into Particle View. And then in Particle View, you just use whatever we were given. Here's how Particle View is defined right now. We're going to change that need to say to work with some kind of symbols that are SwiftUI views. And now we can add a new property there to store whatever symbols get passed in. But slightly more complex is the particle view initializer. This needs to accept a viewbuilder function that generates our symbols. We need to use that as a parameter in the initializer, then store whatever it produces inside the symbols property. Now that we have all the symbols to draw, we shouldn't always pass in the unicorn. Instead, we can just send in whatever symbols the view is given. And now we get to decide exactly what particle image to pass in when we create the particle view. So tagging is done. Or is it? Because we can still make it better. Our drawing code still specifically looks for tag view. How can we make that more flexible? What we're going to do is give our particle system a new tags array property to store all the tags it can use. Then we'll add a tag property to each particle, so each particle knows what it should be drawing. And when we create a new particle, we'll just pick a random tag. Then when it comes to finding the view to draw, we no longer just hardcode the string view. Instead, we use whatever tag the particle has. And now we can just pass in the list of tags we want to use when we create the particle system. The result is identical, except our particle view is now much more reusable. But it's now also possible to use lots of tags and get random particles. And now tagging really is done. Next is coloring. First, I'm going to go back to having our single circle image again, so you can see what's going on. We're going to add a new property to our particle to store whatever color to use for particles, making it white by default. To use that color, we need to modify our drawing code that applies the system's color to whatever is going to be drawn. And now we can pass in a custom color when creating our particle system. Now all our particles will get colored green. And that's coloring done. Next is blending. This is where SwiftUI has a trick up its sleeve. First, let's make our particles bigger and slower, so the screen has more of them. Here's the current code we're using to create our particle view. We're going to make one small change. We're going to attach a blend mode to our circle. Blend mode lets us customize the way views are drawn. The normal blend mode just draws pixels directly, ignoring everything below. But we just made our image use a plus lighter blend mode, which add colors together when they overlap, to create brighter colors. Here, the red, green, and blue overlap to form white. So now as our green particles overlap, they also get brighter and brighter. There's now a hot white in the center. And if we flip the acceleration and use a brown color, we get a pretty great fire effect too. This is just one color, but when you overlap many particles, they get brighter. So that's blending done. SwiftUI is doing all the work for us here. We're just adding an extra modifier to the symbol we're drawing. Now, let's look at rotating. How can we make the particles spin? First, we need to add two new properties to our system: how fast particles should spin and how much variation for spin speed. Each is a SIMD3, meaning it holds x, y, and z values, all set to 0. Then, we need two new properties in our particle, one for the current angle and one for how fast it's spinning. This one doesn't have a default value, therefore it needs to be set. That happens over in our createParticle method. We need to give each new particle a spin speed based on our basic spin speed plus some amount of variation. This means using our spreadHelper method again to get a range of values for x spin speeds. Then the same for y and for z. We can then pass that into our new particle when it's being created. In the update method, we add some amount of spin speed into the current angle, taking into account the elapsed time. When it comes to drawing the particle, we need to create a rotation after moving and scaling. This needs to be done in individual steps, starting by making an empty transform. We then rotate around the x-axis, the y-axis, and the z-axis. And at this point, our transformation is complete, and it knows how to rotate the current particle in all three axes. But actually applying that movement means adding another filter. This time, it's a projection transform filter, and that will contain the transform we just made. And now if we go back to our unicorn example from earlier, we get this. Lots of unicorns spinning on all three axes as they fly out from the center. So that's rotating done. The end is almost in sight. Next, let's talk about shaping. Right now, our particles always come from one central point, but we can change that. We can make a new enum to contain two options, a point and a box. These values are measured in the range 0 to 1, like our other positions. We'll give our particle system a default value of dot point. When it comes to making a particle, we need to decide the position based on what shape we have. When the shape is a point, we just use the system position like before. But when it's a box, we need a random position around our center position. And now we can send that position in for our particle. And now we can go back to our snow configuration, but this time tell it to be full screen width, but 0 height, so it acts like a line. And here's the result. Particles are being emitted across on the screen in a straight line. That's good, but we can do better. Shouldn't snow always fall downwards? To fix that, we need to add two new properties to our system. One store the launch angle, and one store the angle variation. Here's a current way of picking a launch angle inside create particle. It's random, in all directions. We need to replace that with code to pick a random angle, using our base angle plus some amount of variation. But there's a small problem. SwiftUI considers a 0 angle to be directly right, which I find odd. So we're going to make a tiny change so that 0 means pointing straight up. So we'll take our current launch angle and subtract half of pi, which is 90 degrees. Then now, when we create our particle system, we can position it halfway across the screen, but at the top. We'll make it launch directly downwards, but then add just a little bit of angle variation to make it more interesting. And now we actually get some pretty good snow. So that's shaping done. And now all that remains is our last topic. Daddy, do you want to do this bit?
Would you believe that was her very first live talk? Just. So as you've seen, thanks to my wonderful daughter, we've covered quite a lot in this talk already, okay? All these great things here. While working on this talk, we made so many more things. We added things like limiting and attracting and color ramping and spawning and so many things. We could have easily filled a 2-hour talk. But obviously we can't. So instead, rather than just throwing all that work away, I'm really pleased to announce a very new framework called Vortex. High performance, beautiful, magical particle effects for SwiftUI. This shows you all the things you saw at the beginning, the snow, the fire, the fireflies, the magic, plus way more advanced effects. Things like particle bursting to get confetti. Things like multi-stage effects, like fireworks. And yes, of course, you can make it rain and get exactly the same effect Apple has with the bouncing as well. And it's seen on screen, perhaps. Best of all, Vortex is available today, open source for everyone, completely free of charge. Thank you very much.
Wow. Great job, Sophie, and good job, Paul.
Yeah, I tried, yeah. I was there, you know.
So, Sophie, come back up here. So, let's give a really big round of applause for Sophie yet again. This was our surprise of the day, and you know, it takes a lot of courage to get up here. Sophie, at 13 years of age, she's our youngest speaker ever. So give another round of applause, please. So Sophie didn't get an intro, so you're getting an outro.
There you go.
Don't let Sophie's young age catch you off guard. Sophie has been developing in iOS for a few years under very intense training of her father. And last year, Sophie was a finalist for BAFTA's Young Game Designer Awards for her accessibility-centric games. Yeah. In her spare time, Sophie enjoys playing Zelda, paintballing, and also playing with adorable dogs. I think the whole family loves the dogs, right?
Good dogs.
So we are going to do a very, very quick Q&A because we're a little bit late, behind schedule, but we will take a few questions. Also, going forward, you can post your Q&A questions in Discord in the main channel. Anyone has any questions for Sophie and or Paul? Oh, great.
Always got a question. So there was a lot of maths and fairly intense sort of CG context work in what you showed. How usable, how friendly is the resulting framework?
I think it's pretty good. Do you want to see it?
Yes, please.
It's brilliant. We worked really hard on this stuff. Just like literally yesterday, we were noodling around with a new thing. I'll run it back real fast. If I can share my screen. Displays, mirror. There we go. And then Xcode. And then where did I junk all of it? Basically, it's a massive, massive sandbox project somewhere in my huge vortex. There we go. Sandbox vortex, and it's in here. Let's open this up. So you can see the result. Obviously, we've done our best, I think, to try and get the math horrors further out of the way. Most folks just kind of want to use it and see how it looks. So this is a sandbox app. So you can basically noodle around very quickly. And you can see, for example, I'll just press play. You can see it on the screen, hopefully. It's going to build on my extremely not fast M3 Max laptop, apparently. So, for example, in the meantime, it's doing that. I'll show you. Here's what the smoke view looks like. That's literally all the code. Give me the smoke bar system with the shape inside, tagged as that. Here we go. So, here's Fireflies. You saw it earlier. This has been slightly modified. I couldn't resist it with futzing around this morning, actually, because you can now swipe your way through it. I know, right? So cool, isn't it? Yeah. and you want to see the code for that? I mean, the code is absolutely brilliant. What's the code? Fireflies is there. This is, again, if I was bigger. That's the entire view code. So text here, that's the main vortex view. That's my drag gesture. I'm just saying a track to a location, whatever the touch location was, and changing the strength. And that's it. So yeah, it's really nice. And then you get opposite of fire. Fire tracks towards you off your thing like that. So you can control fire. Oh yeah, yeah.
Mesmerizing. We are a little behind schedule, so let's do maybe one or two more questions. Okay, can we do one? Okay, Vina said no questions. I was going to take all your questions. Vina said no questions. Please post your questions in the iOS Conf SG 2024 Discord channel, and this dynamic duo will answer them. Please don't go anywhere yet, because we are going to do a quick photo. Here you go, Vina.